Good morning, everyone. My name is Priska Cushman. I'm past chair of the Division of Particles and Fields, and I have the privilege of welcoming all of you to the final plenary session of this virtual APS April meeting. So we have three very different talks for you about exoplanets, the muon program at Fermilab, G-2 and MUDE, and quark gluon plasma. But they all represent frontiers of discovery, and that's why they're together here. So let me go over some ground rules. Many of you already know these, but for those who are joining maybe for the first time, each of the talks is 30 minutes long with another 6 minutes of Q&A. And to ask a question, you would type your question in the chat box on the live stream, and I'll collect them. So feel free to chat amongst yourselves, but I do request that when you have a question to the speaker, please flag it with a raised hand emoji in front of the text. And that way I can pick them out from the stream. Also, another point, we all want to thank our speakers, but lots of clapping hands filling up the chat box makes it hard to see the questions. So instead, I plan to thank the speaker with my own clapping hands emoji, and then you can all show your appreciation by liking it. So send all your hearts to the speaker that way, please. I will give each speaker a 10-minute warning, and it will be verbal, so it will interrupt, and I'm sorry for that, and then a 2-minute warning. So let's get started. Our first speaker is Didier Queloz from the University of Geneva, who won the 2019 Nobel Prize with Peoples and Mayor with a citation for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. So he will be discussing the rich data we now have on exoplanets, and I'll turn it over to him. Please share your screen.
Thank you very much. So let me share this. And does it work?
Yes, it looks good.
Excellent. Okay. So I will discuss what is about this improving the understanding of the Earth place in the cosmos that we actually did 25 years ago and in the last 25 years. And I will essentially focus my talk to try to explain to you, why this discovery was made possible. The idea is pretty simple: to look for planets around other stars. It doesn't require very complex physics. It's Newton's law, but it's quite of a challenge in terms of technical aspects to reach this discovery. So I will discuss this. Then I will explain why it has completely changed our understanding of the Earth place into the cosmos. Actually, it's even deeper than that. It's a true revolution. So there is a revolution of exoplanet, and I will explain why when you try to fit this into a, let's say, a global formation mechanism to explain the solar systems, we are facing a tremendous challenge right now with all this other discovery that we have been making. And I will describe the many planets that we have found and what are the big challenges for the futures and what we're trying to do to understand all the findings. So to start with, I will just go back to the very basic. A planet is a very tiny object that doesn't have its own luminosities. So you really have to rely on tricks to find the planet. They are, you cannot really see them directly, or very few of them, because only the reflected light essentially you get from the star, but you can detect the imprint of the orbiting planet on the star. So most of the planets that we have found, actually we don't see them. We just detect they are there by looking at the star. So essentially we detect the motion of the star. Here you have a kind of a simplistic picture that indicates our telescopes where we are, and you see that if you can get the light from the stars, you have a Doppler effect due to the motion of the star orbiting the center of gravity of the system with the planet, and that's what you can detect. It's called the Doppler spectroscopy. This is the way we find the first one. You can also be lucky and be in a system where the planet is a line on the line of sight between the star and you, and then you have a transit at that time, and that give you access to the size of the planets. So most of the knowledge we have established is based on essentially these two techniques and a combination of these two techniques. And you will see that we have learned quite a lot using quite a simple approach to find this planet. So why is this so difficult to find a planet? Well, the problem is really the effect you want to get. It's a tiny motions you're trying to get. The effect of Jupiter orbiting our sun is an amplitude change of 10 meters per second. So you have a slow change of the speed of the star. If you observe the star or the sun farther away, you would see this tiny change. So this is the kind of target you have in terms of goal when you want to do that. And it's difficult because it's a tiny effect compared to what you have to detect these measurements. To get you an idea, when you detect a Doppler shift, you use the spectroscopic information you have in the star. So when you have a star like the sun, it's a bit cooler stars in this case, you have really a lot of absorption lines, which is related to all the chemistry element that absorbing a specific wavelength, and essentially it's iron for most of them, the heavy element you see there. And you know exactly where they are, and then you can use all this forest of absorption line to find the radial velocity of the star. The challenge here is the effect of detecting this effect, because each of the line, the intrinsic width of the line is 1,000 times larger than the effect that you want to measure. So you have to rely on a combination of all these lines together, essentially thousands of lines together, to build what we call a cross correlation functions. Or you can see that this is one of them. This is one that the cross correlation functions of the star 51 Peg, where the first planet was detected, which essentially can be seen as an average of all the absorption line you have into the star. So to see that, you need to build up what is called a high resolution spectrograph to see the line. So it's a complicated instrument to build, and come back on that later. And you do see as well, if you just look at the width of the line, just at the width, the full width of maximum of the line, you will realize that what I said, this is 10,000 meters per second. This is kilometer per second, what you see here. So the width of the line is 1,000 times larger than the effect that you want to measure. So if you would move this average line by 10 meters, you would not see anything by eyes. So it's really the challenge here is to be able to do that and to reach these detections. And we need to combine all the line together to see that. And we need to build an equipment which is stable at a level that any change that you would detect will not be due to the equipment. That is really something that was key in the discovery. So the way to do that was to build this machine, which is called LOD. This is LOD. This is a machine that 25 years ago detected 50-watt Peg. I started working on my PhD. I was essentially spending my time on this machinery, helping all the engineers, doing the design work, doing the commissionings, and I was responsible for the whole data analysis to build up the whole data analysis of this equipment. So what you do see in this spectrograph is a couple of key features. One of them, it's a very compact design, which is installed on a very thick and stiff marble table to be as stable as possible. So that's one of the key ingredients in the design of this machinery. Then to reach a compact design, we were using an equipment that you see here, which is a big piece of optic on the left, which is called a grating. And this grating is the first of this category, which is called an R4 grating, which is a grating which is designed to produce an interference pattern, producing the high resolution spectra. And this is the first of them. There's plenty right now of that category because the angle of attack is tangent 4 in this case. And that is the key to have a very compact equipment being built. The second key that provide you the high resolutions and the last wavelength wavelength domain. The second piece of equipment that we have been using is the fibers you see here. You see two optical fibers. Optical fiber are common right now, but 30 years ago, they were barely starting to be used for astronomy. The optical fiber has been designed for computer connections. They're usually working in the near infrared. They were not optimized to work in the visible wavelength the way we would want it at that time. And the first fiber started to be produced for astronomy. And using the fiber was a key trick because you can disconnect from the telescopes. You're not hanging over like most of the equipment used to be on the back of the telescope, on the side of the telescope with all the gravity change. You can have this down in the basement, very stabilized in temperature. And you also get for free a very stable, what's called injection image into the instrument. Injection image is key because the shape at the injections, you see some kind of the shape on the detector later on. So if you twist a little bit the fiber at the entrance, it creates a radial velocity effect, and it's just one of the effects you don't want to get. So this is really the essence of the idea of the equipment is these two ingredients that was key in the design. LOD is the first of that kind of spectrograph. It has been so successful in terms of design, so it has been copied many times right now, and we are building the fourth generations of these instruments. There has been the Harps generations, there has been the Espresso generations. So in US, there is the Esprit generations. There is plenty of instruments that are being built. They all made on the same principle that we established 25 years ago here with LOD. Another ingredient which was key in the discovery, for those of you that remember, was at that time we had a gift, which was the mini computer were available on the market. It was a time when if you needed heavy duty computing, you essentially need to use a mainframe, which is not something you could do in astronomy, in observatories. So you used to bring back with tapes and to go back home and to process the data. That was extremely slow, cumbersome, and didn't make easy reactions to what you were doing in terms of observations. With this mini computer that was inherited from a new kind of a chip inherited from the Cray technology, which is a spark computer, we would be able to process them much quicker. And essentially what I had, was the toy I was playing with. We had the first time 32-bit computer to process this complex image and to try to combine all this amount of information into a single piece of parameter that is essentially the radial velocity. And this was what we achieved with LOD. We had a machine that was providing the required precisions, and we have the tool to process the data such that right after observing a target, so imagine you point a telescope, you do your observation that lasts for 20 minutes, you record enough flux, and then you read the detector, which is a CCD, and you get the radial velocity. So that was really the trick, and that's why by doing that, this is how we identified that a planet was orbiting 51 peg, because we were having a machine that was from the day one absolutely on the spec and performing the way we had in mind. So in a way, we started quite late compared to other teams, but we catch up everybody because of all the tricks we have been using with this machine. So the big news came barely 1 year after operating the program, and it was to a surprise because it was such a surprise that in essence the program started. My supervisor was aware, and I got this planet. I mean, as in a way as a gift. I was surprised by getting this planet because it was not expected at all. And the reason why this planet wasn't expected at all, it was the nature of that planet could not exist. In a way, the planet was impossible. We find a planet of Jupiter mass, but this is a copy of the abstract, but the orbit of the planet, the semi-major axis, was only 8 million kilometers from the stars, which is 20 times closer to the orbit of the Earth, which is within the orbit of Mercury, which is 100 times shorter than the orbit of our own Jupiter. So that was a serious problem. That would explain why the planet, nobody was expecting that. So we come up with the idea that the planet has to have moved, we said migrated, or maybe the planet, the object was bigger there and gets stripped out. It's what's called the brown dwarf. Actually, these two elements that I'm mentioning right now has been detected. We know that planets, they do migrate. You will see later there are plenty of them right now. And we also know that some of these planets are being stripped out because they're close to the stars. And in a way, it was a kind of visionary statement we had in the paper without any really background to explain how it may happen, except that just general principle. It was right on the spot that the whole field was filled of that kind of objects. So why that planet was such a surprise, and what this planet was such a revolution at that time? Well, to understand that, you have to go back to understand the formation of the planet. So the planet is understood to be formed inside a disk that we call a protoplanetary disk. You see here a wonderful picture that is obtained by an interferometric array of millimeter telescopes on the Altiplateau in Chile called ALMA. And what you do see here is the thermal emissions, not very much, 20K about here, of tiny dust grain or pebbles that you have in a disk shape orbiting a star. What you don't see is the gas. The gas is not visible here, but you have for one part of dust and pebble, if the star is young enough, you have at least 100 times more gas, hydrogen and helium, that comes with this. This gas and solid structure is a key ingredient. That is the key to the mystery of the formation of the planet, and the reason why people were convinced and still believe that giant planet needs to be formed away and cannot be formed next to the star. What you have to imagine is the fact that you are in this structure with gas and solid depends also on another parameter that you don't see here, or you see it implicitly, which is the temperature. If you go closer to the star, the temperature will be higher than farther away in the disk. Well, this has an impact because what you do have when you change the temperature in the disk, you have a phase transition from gas to solid. So what you have to picture is you have gas, water, CO2, CH4, CO, N2, all this kind of gaseous material, molecular material that you have that is in gaseous form. If you cool it down enough, it will not be a gas anymore. It will become solid particle. And if you want to make it simple, it becomes snow. It's CO2 snow, water snow. This is what we call snow line. And this snow line is absolutely essential because when you decouple the physics of a solid material, of a gaseous material, you don't follow the same rule into the disk. Essentially, you're losing what's called the hydrostatic equilibrium. So when you have a gas, you're sustained by the hydrostatic equilibrium. When you remove the gas, it just falls on the mid-plane because you don't have this hydrostatic equilibrium to be sustainable. So if you look to a planetary disk seen on the side, this is another picture. It is a picture of a nearby star called Beta Pictoris, visible in detected visible by the Hubble Space Telescopes, and it happens to be right on the edge. So what you do see here is a thin, narrow set of these dusty particles that you do see on the thermal image. And the reason why I show you this picture is for you to understand that all these tiny particles are setting down all together on the mid-plane. This is the formation of the planet. You're moving from a situation where you have a lot of material spread apart, when nothing much is going on, into a point when everything is setting down on the plane at a specific distance, depending on the material you're considering. And there's so many material here, they're bumping into each other, they're gluing into each other, and they form the core material where you start accreting the planet. And this core material is essential, and it was one of the key discoveries in the 70s when people realized that there is a core part on the giant planet and also the ice giants in the solar systems of about 10 times the mass of the Earth, and that's how you make the core. You only do that when you have these phase transitions, and the closest phase transition possible is the one from the water. You cannot find anything closer. Anything closer cannot experience a phase transition. You have material closer. This is how you make planet like the Earth, a lot of silicates, for example, but you don't have this massive reservoir of gas that can use to form material. And the fact you have 100 times more gas available makes when you do the phase transition of all the gaseous molecules, you have 100 times more material to build the core. This is why you have this big core. This is why you form a giant planet beyond the snow line. This is why nobody was expecting a planet like 51 Peg. And it has been an absolute shock for the community. And it took a couple of years for people to be convinced that this planet was actually real. What happened is 4 years after the discovery, the first transiting of such a what we call now hot Jupiter was detected. And then that was the end of it, because then it was obvious that the same planet with the same model could be explained the same way, coming from a drastically different techniques, which in this case was just the fact you have the shadow of the planet passing in front of the star. So in that sense, 51 Peg was an absolute revolution in a way that is pointed the finger on a preconception that we had about the big planet in the solar systems that turned out to be wrong, which is when you form a planet in the solar system, the planet stays where it is. Actually, the planet can move. And what happened in the last 25 years, it was even worse than that, because we have found that a lot of planets actually are moving. And if it's not the majority of the planet, and then the question is, where do we sit into this? So to understand, I just want to mention the Jupiter probe that has probed these discussions about the element here. Now, this is a complete summary, an outlook of all the planets that we have found with these two techniques I was mentioning, transit and Doppler spectroscopy. You get different kind of information. In one hand, you get the mass, the other one, you get the size. Some of them have both. Some of them have only a Doppler spectroscopy. In that case, it's a minimum mass. But altogether, this is the kind of double picture you have, and you have the period of the systems. I just identify Jupiter and identify Earth to make it simple. So let's start on the left side. So on the left, you do see all these planets that have the size of Jupiter, which is 10 times the size of the Earth, which have short period. They are the light blue. The reason why it's light blue, it comes from the ground-based survey looking at transiting planets. Now, this is where sits 51 Peg. To find 51 Peg, you have to go on the other diagram. In this case, it's a mass. The same period, the same population is here with about a mass of 300 times the mass of the Earth, which is about the mass of Jupiter. This is where we see the hot Jupiter. If you do the statistical analysis, which you cannot do on this diagram because it's full of biases and threshold here, you would realize that the occurrence of such a planet is between 1 to 4%. It means when you observe a star in the sky, you know that you have 1 to 4%, and depends a little bit of some ingredient in the stars, to have an orbiting 51 Peg, like a hot Jupiter planet. So in a way, the reason why we picked up that object was just not by luck, it was because it was expected. We had about 100 stars in the sample, and actually we had 2 hot Jupiter in the sample, and 51 Peg was the first of them. And we've been quick finding it because we had an amazing tool working from the day one like a perfect clock. So this is about the hot Jupiter. They are not that common. So in essence, the fact that big planet like Jupiter can migrate in, it's rare. But what has been an absolute surprise, in the last 25 years, we have improved the sensitivity of the discovery of the detections, both on the ground, on Doppler spectroscopy. We have flown a tremendous spacecraft called Kepler. We're flying tests right now. There's been a lot of progress, and we have identified that populations, which is anything which is below Jupiter, which what we call usually super Earth or mini Neptunes or Neptune or mini Saturns, and they're all sitting in periods from less than a day up to 100 days here. And essentially, all these planets are within the orbit of Mercury. And what is the big shock in this is when you do the statistics and you ask yourself, what is the likelihood that you will pick up one of this object. Quite a lot of them are in systems, by the way. It's not only one planet, it's many planets orbiting. And because of the proximity of the period, they tend to be what's called in compact systems. So we used to call that compact super Earth systems. Is of the order of 50 to 80% of the stars. So essentially, the majority of the star, which are like the sun, if you want to make it simple, have planets of that kind. And I think this is a revolution bits because they're not like the solar systems. So if you invert the statistics, we already know that we are not the majority in terms of solar system. And that's a dramatic twist because 30 years ago, you would ask anybody would be looking for Jupiter, at the orbit of Jupiter, not for these populations. So the piece of luck is nature is different. There's a lot of migration going on in the formation of the planet, and we understand why, because there is a coupling between the gas disk and the planet. And there is theory developed in the 80s to understand the satellite of Jupiter that has been developed by astronomers, but they were never looked seriously enough in a way that they will be able to relate and predict anything here. But that what it is reality right now. We have this population of planet. Now, the other interesting aspect is we have detected in Doppler program also more regular Jupiter, about 10%. A bit fraction of them are in a kind of awkward orbit. They're not in circular orbit, but there is some hope that the fractions of this Jupiter planet that we have found in Doppler spectroscopy may be the kind of counterpart of the famous Jupiter that everybody had in mind 30 years ago. No,
10 minutes.
sorry. Yep, that's fine. Thank you very much. Now, the interesting bits of this diagram is when you combine the two. You combine the mass informations with the size information, because then you get access to what is called the bulk density. So when I do that, we have about hundreds of planets for which we have both. So we have an exact mass and we have an exact size, and that's how it looks like. So when you add Jupiter on the top of it and you add Neptune's and the Earth, that's what it looks like. So you have this hot Jupiter populations, mass of Jupiter, size of Jupiter, and you see they are mostly all of them, they're above Jupiter, which in terms of density means they are lighter than Jupiter. Jupiter is slightly more than water in bulk density. This one are slightly lighter. If I draw the water density line, this is the bulk density of the water, 1 gram per cubic centimeters. You would see that essentially all the hot Jupiter we have found, there seems to be slightly above Jupiter. Saturn would be above Jupiter, would be there. So in a way, it's not something extraordinary. We have some object which is a bit exceptional, and we do believe that this is related to the fact that they are so close to the stars that it is modifying, is changing a bit the internal structure of the planet in a way to make the planet more puffy. That's what we have. Now, the interesting discovery is when going down to Neptune, we have a population that have no really counterpart in the solar system. Some of them are above Jupiter, some of them are below Jupiter, to have this kind of diversity of giant planet down to ice giants. But the big shock is as soon as you get down to what's called the mini Neptunes, or depending if you want to come from the other side, from the super Earth, you have a big spread of density. This one is light in density. This one is heavy. This is the mean density, mean bulk density of the Earth here. So we get an idea that we have object of a couple of times the mass of the Earth that seems to have a bulk density like the Earth. So they may look like core or Earth-like object, if you want, meaning that we don't really sure it's Earth-like, but at least Earth-like in terms of bulk density. While at the same time, we have object that seems more alike, still of the same small mass, but more alike Neptune's, or even some more like Jupiter, which means they have a massive amount of gas. The fact we have this diversity is not well understood, but there is a common understanding that as soon as you reach a mass of 10 to 20 Earth mass, the object is massive enough if there are enough gas around to capture a lot of gas. So the fact you don't have very much dense object there is not a surprise, because the object is massive enough to capture all the gas and end up there. So this is a big challenge for the future, is to understand that. What are we talking about? And to give you a little bit of a picture, we have Jupiter, we have Neptune, we understand very well with the core and then the envelope. So the small object we're talking about are of that kind. We have Earth object, we have superdense Earth, we have super Earth or mini Neptune object, some of them possibly with a thick atmosphere. And the challenge is right now is to get to this atmosphere, to try to measure this atmosphere, to get an extra dimension parameters. To do that, we can use the transit, because a transiting planet with a thick atmosphere would leave a trace that we can get with telescopes. And the telescope we are very fortunate to have is the big equipment we are using, the big toy of astronomers. One of them is the soon to be launched James Webb Space Telescopes. It will essentially be doing this. It has a capability to detect molecules using the transit and using a tiny difference in the transit depending on the wavelength with the fact you are out of space in the infrared. You can also have partially the reflected light from the planet. On the ground, we're building the biggest ever telescope of 39-meter diameter. You see the size of the car here to give you an idea. It's in Paranal, Chile. This, you can combine it with a high resolution spectrograph, and you can do exactly the same. But in this case, you get access to different molecules, and you can even get some idea of the wind or dynamics going on into the atmosphere. And all this is without seeing the planet. It's just by remote discovery, just the fact with the transit and indirect discovery of the planet. Now, there's also a big push to detect what's called the Earth twin or the Earth equivalent. You may have noticed on the discovery that there were no planet within the Earth-like regime. It's not because we are not trying hard. It's not because they don't exist. It's because we have failed right now to discover this planet, essentially because first, you're so close to the instrumental limit, so it's a real challenges, but you're also very close to the intrinsic noise limit of the star. The star at that level produces a signal due to the fact that the atmosphere is kind of bubbling, and this bubbling of the atmosphere becomes a limiting factor in discovering these planets. And there is a new program called Terranting Experiment, which is meant to discover this called the missing link with this planet that everybody had in mind when we started the program, which is a planet like the solar system. You see that we came back 25 years ago by detecting an awkward object. We have found even more awkward objects. This forces us to rethink where we're sitting in terms of systems. And then there is a related question here, which is the fact that we have an Earth planet on these systems, and how likely it is to have an Earth planet. And does that mean that we have to have a similar Earth planet to also have life? Is there any way we can find out about the nature of the atmosphere of this planet, knowing that Venus and Earth are very close together? It's not very obvious to find out just by using the bulk density which one is the good one to find life. So all these questions now is bubbling into the community because we have so much diversity into the planetary systems. So we're trying to order that and trying to understand what exactly is the element that drives the formation of these compact systems, and what is the element that help systems to be like this system like our own. And that's, I think, the big challenge for the next 20 years. Thank you very much.
Okay, thank you. That was great. We've got a couple questions here. People can also add some more questions to the chat if you like. The first one was early on by William Snow. Were you developing this improved optical spectroscopy specifically with exoplanet searching in mind?
Yes and no, because 30 years ago, I think nobody would have built a spectrograph like that with only exoplanet in mind, because that was a weirdo field. Nobody would do that. So we did it in mind of detecting any smaller orbiting objects that at that time, what was very fashion is what we used to call brown dwarf, which is failed stars. So the incentive was essentially to explore that. In my PhD, I had no mention into exoplanet at all, but because we've been working well, the instrument was capable to detect smaller objects. So at the end, when we put the proposal on to get access to the telescopes, we explicitly, with Michel, stated that we are going to explore the population of orbiting objects in the substellar regime, including planet. So in a way, we didn't build the instrument with a planet in mind, but when we realized the instrument we had built could do it, we designed a program to be capable to find a planet.
Great, thanks very much. There's a second question here. Pablo Giuliani says there seems to be two clusters in the data of M versus R. Do you have some sort of intuitive explanation for that?
Yes, there is a lot of element into this diagram, but we have to be a little bit careful because it's a composite diagram with different survey time, with different limitations. But there is an understanding that finding the big short period planet is easy. So you have a lot of this hot Jupiter that has been found because they are easy, and there is less of objects smaller. So first you have this first effect that having more objects easier find on one part of the diagram compared to another one creates the perceptions of the two populations. So we have to be very careful about that. No, there is a reality when you work through the statistics that indeed there are structure into this diagram. They are what we call valley. And the reason why there is a valley is exactly for the purpose I was describing to you. As soon as you reach a given size or given mass, it happens that it's easy to capture the rest of the material around. And actually, it's extremely fast, while it takes forever to reach that level. It's a very slow, gradual process. The problem is the initial stage needs to fight against the inflow of energy falling into the planet, which is being built up, and the release of this energy that prevent the temperature to goes up and then to lose the material you bring up by just thermal kinetics. So it takes a long time to do that. But as soon as you reach this level where you fight anywhere, the gravity is so strong that whatever thermal you reach, you will never fight the gravity, then anything falling stay. And this is why you have a very fast buildup. So this explains the fact that there is little objects that are within the regime between Neptune's and Jupiter or Saturn-ish because of that reason. And then the end mass you're reaching into a planet buildup just depends on the amount of material you have. So it depends on the nature of the disk you have. Some disks have more gas than other. And once you have exhausted the gas capture, all the material is on the planet, that's it. This is why you end up with a planet of a given mass. In the solar system, it is understood that Saturn is smaller than Jupiter for that reason, because there is less material available to grab at the Saturn orbit than at the Jupiter orbit.
Thank you. We have time for one more question. This one's from Christopher Gold, who asks, how well understood is the migration mechanism?
Well, the migration mechanism is pretty well understood because it's a very natural effect between the response of the disk gravity. What happened is the planet is creating waves, density waves, sorry, and these density waves create gravity waves back into the planet. That was pretty easily to understand. The challenge of the migration theory is to explain how do you stop? Because it's easy to migrate, and actually it's pretty quick to migrate, but how do you stop the migration mechanism preventing the planet to fall into the stars? And this is a bit less understood. People are arguing that there is a lot of magnetic field when you get closer to the stars. The disk has to stop at some point, so there is no ways to maintain, to sustain this gravity push. And because of the magnetic link you can hold the planet there. So it may be a combination of various effects, which is combined with the kinetic of the disk and the magnetokinetic of the disk at that distance. But that kind of very short distance to the disk is poorly understood. And there is certainly a possibility, and it's very likely, that some of these planets that migrated it ended up into the stars at the end, because the stopping mechanism was not efficient enough to stop it. But at least some remained, and a planet like 51 Peg in somewhat was successful in the stopping mechanism.